Let's extend on our idea of projectile motion, which of course we saw in extension 1, but now we can play with it a bit. I'd throw this question first up actually, because it's a fun little question. A stone is thrown so that it will hit a bird at the top of a pole. However, the instant the stone is thrown, the bird flies away because it sees, hey, you're trying to hit me with that stone? Starts flying. But it's a stupid bird. It flies away horizontally in a straight line at a speed of 10 metres per second. The stone reaches a height double of the pole, and then as it comes down, it hits the bird anyway. Find the horizontal component of the velocity of the stone. So the reason I say the bird is stupid, it should have flown towards the person throwing it, not away from the person throwing it. We'll assume there's no resistance. In that case, we know projectile motion is a parabola. And the reason I'm using this example is to illustrate, well look, sometimes just our knowledge of quadratics can solve these problems rather than using all the calculus and what have you. We know the greatest height will occur at the vertex of the parabola. So I'm just going to call that vertex 0, 2h, so twice the height of the pole. That therefore means, because I've made the vertex at an x value of 0, the equation of the parabola must be y equals 2h minus some constant times x squared. It's an upside down parabola. Okay? So there's a picture of it. Right? So we know that the path, I'm aiming for the bird on the top of this pole, which has got height h, and it'll come down and end up hitting the bird as it's flying away over there, also at height h. So what do we know then? We know that when y equals h, h will equal 2h minus kx squared. So I can now find the x value of the pole, but also the x value of when it hits the bird as well. It's going to be plus or minus root h on k. So there's our 2 points. I now know the total distance the bird flies. So it must fly 2 root h on k metres. And we know it's flying at a velocity of 10 metres per second. So I now know how long it takes for the bird to get there. Time equals distance over speed. Subbing that in, all right, it'll take 1/5 root h on k. Now when y equals 0, that's when it lands on the ground here. If it didn't hit the bird, I suppose, so it missed and got the ground. 0 is 2h minus kx squared. I now know the x-intercepts of my parabola. I can now work out how far the rock that I threw, it's gone a total of root 2h on k plus the root h on k when it hit the bird. That's how far it's gone horizontally. Speed equals distance over time. I can now work out the speed. 5 root 2 plus 1 metres per second. So there's the horizontal velocity of the stone. I didn't have to use any calculus, it was just using my knowledge of the quadratic. That's a nice little question. Let's have a look now at projectile motion, but adding into it this idea of resistance that we look at in extension 2, the 2021 question. Particles projected from the origin, initial speed, u, angle of theta, so your standard sort of projectile motion question. Particle is subject to an acceleration due to gravity, and so on. So in this case, actually, there's not resistance involved, or it doesn't appear to be. They've given us a displacement equation. So we don't have to go and work those out, I guess is the point. They've given us those to work with. And just to highlight that, they say, don't prove this. For some values of theta, there will be 2 times during the flight when the particle's position vector is perpendicular to its velocity vector. Find the values of theta for which that occurs, but then also you have to justify that they will occur during the time of flight. There's the displacement one they gave me, so I can work out the velocity one. I just differentiate each component. So I've got u cos theta and minus gt plus u sin theta. They've told me those 2 vectors are perpendicular, therefore their dot product is 0. This wonderful expression, u squared t cos squared theta plus a half, g squared t cubed minus a half, gut squared sine theta minus gut squared sine theta, plus u squared t sine squared theta equals 0. Tidying that all up, we have an equation here. But one thing I do know is that t is greater than 0, because the time of flight. Why is that important? Well, because I can just divide through by t. I know I'm not dividing by 0, because t equals 0 is not a possible solution to this problem, which means I now have a quadratic to solve. They've told me there are two distinct times this happens. If that's true, then the discriminant of that quadratic must be greater than 0. Here's my discriminant. 9g squared u squared sine squared minus 8g squared u squared. Okay, well, g was a constant. That's our gravitational acceleration. U is a constant. That was our initial velocity. Divide both sides, therefore, by g squared u squared. I now have a little trig inequality there. Sine squared theta has to be greater than 8 on 9. That tells me that 8 on 9 is less than sine squared theta is less than 1. Why can I say that? Because I know theta has to be acute. That's our angle of projection. So I know I'm not going to get negative answers, so it must be between those two. Therefore, the square root of 8 on 9 is less than sine theta is less than 1. Theta is in between the inverse sine of 2 root 2 on 3, which is approximately 71 degrees, and 90. So somewhere in between 71 and 90. Now, when does it hit the ground? Because remember, we have to show that our values will happen within the time of flight. So I need to know what is the time of flight. Particle hits the ground when y equals 0. Ends up being 2u sine theta on g. So both values of theta must occur when t is in between 0, can't include 0, but it could include 2u sine theta on g. I suppose it could happen when it hits the ground. Yeah, let's go back to our equation and find the two values of t and hopefully show that they are in between these two values. It's a lovely expression we have to solve here, but can simplify it a bit. Square root of g squared u squared is of course gu, so I can factorise that out of the surd. Then the g will cancel with the g squared, leaving me with just a single g on the bottom. Now, I'm going to say this. Have a look at the top of that fraction. I'm just looking at the negative bit, the 3u sine theta minus the root 9 sine squared, etc. That has to be bigger than 3u sine theta minus u, the square root of 9 sine squared theta. That would end up being a bigger number. If you have a look at the right hand side, the square root of 9 sine squared is 3 sine theta. So in other words, what we're saying is this expression is greater than 0. Well, that's good. We want the time to be greater than 0. So we do know that both of the times are positive numbers. I don't obviously have to check the plus one because that's going to be positive because you've got a positive adding another positive to it. Well, let's now work out what the bigger one is. Remember, we need it to be less than or equal to 2u sine theta on g. If I know the bigger one is, then I don't have to worry about the smaller one. So the larger one would be 3u sine theta plus u on the square root of 9 squared theta minus 8. Now this time I'm going to say, well, that's greater than 9 sine squared minus 8 sine squared. That's nice because now I get 3u sine theta plus u sine theta, which is 2u sine theta, and that was the other end we were trying to prove. So yep, both of those times will occur during the time of flight. So I can now go back to my angles and say, well, those two angles must happen in between 71 and 90 degrees. Let's have a look at last year's one. Particle of mass 1 kilogram projected from the origin at an angle of 30 degrees. Using that information, show that the initial velocity is this. We have to show that. All right, we'll draw up our components of velocity, and x dot ends up being 20 root 3, which is what we're expecting, and y dot ends up being 20, which is what we're expecting. I think the key with this question is, because it is show that, you need to, whether or not you draw a diagram, but you can't just simply go, oh, well, x dot will be 20 root 3 because of the standard v cos theta and what have you. You've got to show how you get it. Now we're throwing resistance into our projectile motion question. So the force is acting on the particle. Yes, we do have gravity, but we have air resistance as well. And that resistance is proportional to the velocity, and that constant of proportionality is 4. Gravity, to make life a little bit easier for ourselves, it's going to be 10. The position vector of the particle at time t is r, and the velocity vector is v. Show that v is that expression. So we've got to work out the velocity vector. Even in the most simplest of questions, still draw a force diagram so you can get your head around the problem. So for this one, I'm saying horizontal forces. It has air resistance of 4. Well, 4 times the velocity. Vertical forces. It has the force due to gravity, but it also has air resistance as well. But of course air resistance happens in all directions, and it's the same in each direction 4 times. So it needs to be included in both. And I guess that's also why drawing up a simple diagram helps you with that, because you're putting the forces on it and you'll see it, that, oh yes, I've got this resistance I've got to take into account. Let's go back to our horizontal forces. The mx double dot will be minus 4x dot, so divide through by the mass. Okay, it was a unit mass, so that's why the m can just goes away. And then over in the y direction we end up with minus 4y dot minus 10. Okay, we want to show VT. Alright, bit of integration to do, and the log, there we go, comes out nicely. So 20 root through e to the minus 4t. Now let's do the vertical one. Again, separate out those variables, bit of substitution, and we get the other result that they were looking for. When it comes to your setting out, some people tried to leave it inside the vector itself and do it all in one hit, and so had plus a constant here and all sorts of weird things. Don't make life hard for you, so it's just easier to break it into the 2 components, work on the 2 components separately, and then just recombine the vector at the end. Now they want us to show the displacement vector, so basically we're going to do the same thing. We'll just go through and integrate again. So there's dx to t, separate out the variables, and there's our x component to y to t, separate out the variables, and there's our y component that they're looking for. Okay. Now comes the interesting part of the question. They gave us these graphs. Y equals 1 minus e to the minus 4x and y equals 4x on 9. Using that diagram, find the horizontal range of the particle. Well, we know it hits the ground. The way I've put it there is still using vector notation. I don't know where, so I've left the x value as x. I don't really need to know it, because what we're interested in is when is y equals 0. So let's just look at that component. So the 45 on 8, 1 minus e to the minus 4t, minus 5 on 2t, that has to equal 0. Now if we play around with that, look what we get. 1 minus e to the minus 4t is 4t on 9. They're the 2 graphs they gave me. And they've told me they intersect approximately at 2.25. So I don't need to do any work. I could just read off the graph and say, oh well, from the diagram, t it's approximately 2.25. There's my answer for the time. So if I substitute that in, I can now go and find what x is, that horizontal range. And to 1 decimal place, that's 8.7 meters. So 6F and 6G